I'm Valentin Touzeau from Grenoble-Alpes University, and I will talk about uncertainty in cache analysis, how we can remove it or detect it to speed up the analysis. So here are two examples of domains that make use of cache analysis. So the first one is real-time systems, because in addition to be logically correct, these systems need to guarantee that will terminate in a bounded amount of time. And because caches introduce variability in the execution time, you need to analyze them in order to derive precise bound on the execution time. The other example is security, because it has been shown that an attacker can retrieve partially or completely the secret information manipulated by a process by querying a cache that is shared between the victim process and his own process. So a cache is a small but fast memory located somewhere between the core and the main memory. And it is usually split into different cache sets. And one block can only map to one of the cache sets. So in the term of analysis, you can analyze them completely separately, and everything works as if you have only one cache with a single cache set. So when you're accessing a block, you basically first look in the cache if it is present, and if it's not, then it's called a miss, and you look in the memory for loading the cache and for loading the block in the cache, and this way you can avoid further costly access to the memory. For example, if the block is already in the cache, then you do not need to access the memory again. So you can classify block accesses in three categories. The one that always leads to a hit, whatever the execution path is in your program, which is, for example, the case for this one. Conversely, the one that always leads to a miss, for example, because it's the first time you access it. And the last category is the blocks that sometimes lead to a hit and sometimes lead to a miss, depending on the execution path. So there already exists some analyses that are able to soundly classify some block accesses as always hit or always miss, and that are called must analysis and may analysis. And they are sound but incomplete, meaning that there exists some blocks that are always hit or always missed that are left unclassified by this analysis. And so you end up in this situation where you cannot tell anything about blocks that are left unclassified. So our aim is to remove this uncertainty, and our idea was to use a model tracker to more precisely examine the execution path. But it does not scale very well if you do it naively on this large amount of block. So we first designed an analysis that soundly predicts that some blocks are, that there exists a path leading to a miss and another leading to a hit. And finally, we can run the model tracker on the remaining blocks to remove completely the remaining uncertainty. So one of the main aspects you need to take into account when performing cache analysis is the replacement policy, because when you want to load a block into the cache and that the associated cache set is already full, you need to choose a block to evict, and this choice is done by the replacement policy. In our case, we will focus on the least recently used policy that you can find, for example, in the MPPA of CAV. And that works by keeping the blocks sorted from the most recently used to the least recently used block. And so it maintains this order across the different access you made. So for example, if you access a block that is not in the cache, you will load this block at the most recently used position, and you will shift the age of all the blocks by one, evicting the least recently used blocks. In case of a hit, you simply load the blocks that is accessed to the most recently used position and shift the blocks that were younger in the cache. And so this analysis, this replacement policy is one of the easiest to analyze. And the analysis I mentioned before was proposed 20 years ago. And they work by maintaining both a lower bound and upper bound on the block's edge. So for example, the May analysis that is used to predict misses keep a lower bound on the block edge. So for example, if on one path it tells you that the edge of a block is at least 1 and on the block it's at least 3, when path merges, you need to be conservative and keep at least 1 for the new bound. So here is how it performs on a quite simple program. We have only one condition on which path splits and then merge again. So after performing 2 access to A and B, what you can tell, for example, is that A has blocked at least 1 because you access B in the middle. You can do the same on the right path, and then if you need to merge the path, and as previously you keep the minimum bound. So for example, in this case, if it tells you that whatever the execution path you take, A has edge at least 1. And this tells you that for some blocks, they are always missed. They are guaranteed to be missed at the execution because they are not in the May cache when they are accessed. For example, C is not in this cache set, in this cache state. So it's guaranteed to be a miss. You can perform the must analysis in a similar way by keeping an upper bound instead of a lower bound. And this will classify some other blocks as always hit, which is the case for B here, because it is not evicted since the last access. But these 2 analyses leave our 2 last access unclassified. And so before running the model tracker, we try to classify them as definitely unknown by our new analysis. And so the idea is similar to the May and must analysis. We compute lower bounds and upper bounds on block edge. But instead of maintaining blocks that are valid for every execution path, we only keep bounds that are valid for at least 1 execution path. And so this gives us bounds that are more precise than the equivalent in the May and must analysis, but they are not valid on every path. And that's not a problem because we only want to ensure the existence of a path leading to a hit and another leading to a hit. For the ones that know about it, it's an example of what are called the hyperproperties. So here is how it performs for the exist-miss analysis on our examples. So it runs similarly than the May analysis, but this time when you perform the join, you can keep the maximum instead of the minimum of the 2 bounds. Because you only need the bounds to be valid on one of the 2 paths. And so in this example, it will tell you, for example, that A is at least edge 3 on at least 1 path, which is the right one in the example. And so this tells you, for example, that there exists a path leading to a miss for this access to C. Which is the left one because there is no previous access to C on this path. You can perform the exist-hit analysis in the same way, and this will tell you that there also exists a path leading to a hit for the access to C, and so you do not need to call the model tracker on this block because it's already classified, and the model tracker would find exactly the same 2 paths leading to a hit and a miss. So finally, we are only interested in using the model tracker for this last access that is left unclassified. So this step is done by model checking, as I mentioned. But we run the model tracker 1 time for every block that is left unclassified, and this allows us to make abstraction that is very efficient for the model tracker, because we only keep information that are useful to classify A as a hit or a miss, And in the case of the least recently used policy, keeping the set of younger blocks, the set of blocks that are younger than A is enough. So, for example, in this cache set, we only keep the information that B and C are younger than A, and we do not keep the information that D is in the cache, and we do not keep the information that B is younger than C. If A is at the most recently used position, then the set of younger blocks is simply empty. And in the case that A is not in the cache, we use a special value epsilon. So here is how it works on our program. So we start from the empty cache set. Then when accessing A, the set of blocks that are younger is set to empty because there is no blocks younger than A, because A is at the most recently used position. Then across the different accesses to B, C, and D, the set of younger blocks is updated. And when joining path, you need to keep all the possible values for the younger set. And by doing so, it will tell you that A is always in the cache. And it is a hit because it can be edge 2 or edge 3, but in both cases, it's still in the cache. So we evaluate we implemented these two analyses into a prototype that is built on top of the LLVM framework. And we only analyze instruction caches because analyzing data caches would require performing first something like pointer aliasing analysis and stuff like that. So analyzing instruction caches was much simpler for our prototype. And we run it on the Tackle benchmark suite that is usually used in the worst case execution time community. So we first evaluate the precision of the model checking phase by looking at the number of blocks that are additionally classified by the model checker. So on the x-axis, you have all the program on which we run our analysis. The smallest one are here and the biggest one are here. And on the y-axis, you have the improvement in the rate of blocks that are classified as always hit or always miss. So this shows that for some benchmark it performs quite badly. This is mainly because for some of them, the may and must analysis already classify everything. So there is no improvement possible. But for some other benchmark, we have much better improvement up to 1/3 of the blocks. And that is very interesting because it can also speed up all the analyses that are using the cache analysis. Then we evaluate the speed up due to the use of the definitely unknown analysis by comparing the number of calls to the model checker we actually made and the number of calls we would have made without running the definitely unknown analysis. And this shows that we run from 10 times to 100 times fewer calls to the model checker by running the definitely unknown analysis. And that allows the model checker phase to scale much better. Okay, so to conclude, we have two different contributions. First, an efficient cache model that derives an exact analysis, an exact classification, because in our examples, we know exactly what are the possible edge of the block A after running the model checker. And we have also a new analysis that is able to eliminate some blocks from the model checking phase by already finding a path leading to a hit and another leading to a miss. And as future work, we are looking at connecting these two analyses into a worst case execution time estimation tool. and into extending it to other replacement policy, but that seems quite hard for now. Okay, so if you have questions, I will be glad to answer. Thank you for your attention.
It looks that the same method could be used also for multi-level caches, is it right?
Sorry?
For multi-level caches, could I use the same approach?
Yes, you can use the same kind of approach for multi-level caches. The problem with multi-level caches is that when you have uncertainty on the first level, for example, if there exists a path leading to a hit and another leading to a miss, you don't even know if you have an access to other levels. And there is currently some analysis that work by abstract interpretation to analyze the multi-level caches. And you can have also trouble because on one path the block is, for example, in the L1 caches. On the other path it is in the L2. But so you know that the access will hit in one of the two levels. But when you join the path, if you do it conservatively, you should tell that it is neither in the L1 level and the L2 level. So it's harder to analyze, but there is some analysis that do it, and we did not look for the moment to implement it using a model checker.
Hello. We're curious about the running time and the size of the benchmarks. What kind of...
Okay. So for the size of the benchmark, okay, so for the bigger program, we have thousands of memory blocks and memory accesses in the program. For the smallest one is something like 10 memory blocks, which is what just a recursive factorial, something like this. So for the running time of our definitely unknown analysis, it's very similar to the May and must analysis, and it's quite instantaneous compared to the model checking phase. For the model checking phase, we put a timeout after 1 hour, and this timeout was reached in 3 of the program of the benchmark, I think. And for the other one, most of the time it performed in less than 5 minutes, and for the few remaining, it's somewhere between 5 minutes and 1 hour.
Thank you.